I'm really excited to welcome you to the NGSS Assessment Academy. In part 2, we're going to cover COVID-19 and clusters. We're going to talk a little bit about just sort of the framing that we've heard from district leadership around assessment during COVID-19. And then we're also going to talk about clusters. My name is Brendan Finch. I was a high school and middle school teacher for a while in Los Angeles. I taught for LAUSD, Los Angeles Unified, and also charter schools, so KIPP, Green Dot, and CAVA. Really excited to share what we've been building with you today. If you have any questions about what we're covering, please send me an email. It's brendan@InnerOrbit.com. And I'd love to answer questions just about NGSS assessments or about our website, InnerOrbit. I hope it is helpful to everyone, and I'd be grateful for any of your feedback that you have as well. So what we do for InnerOrbit is rigorous NGSS assessments. So we write assessments for grades 6 through 12. We will likely add grade 5 by the end or by the beginning of the school year. It's totally free for teachers and students until August 2020. If you're looking for phenomena or assessments, check it out. We have hundreds of phenomena and thousands of assessment items. That's InnerOrbit.com. You can go on, check it out, totally free. And we have lots of phenomena that are visually engaging. The goal right now is mostly data collection, not generating grades for students. So if you go on our site, you'll find a database of these phenomena. We use GIFs or GIFs, however you think that word is pronounced, and collect them together and write clusters of questions around them. We also do custom NGSS assessments. So we'll take our database, and if you send me standards that you're working on either in your own classroom or through district partnerships, this is what we do. So we'll set you up with a custom assessments based on the instructional segments or units or lessons that you're working on with our database. We often write new questions for districts that we partner with, and we would love to help you in any way that we can through this time. So today we're going to talk about a few things. We're going to review good phenomena and sense making. That was the goal of the last NGSS Assessment Academy. We're going to talk about using DCIs for background knowledge. We're going to talk about the K-12 progressions. We're going to talk about evidence statements. Yeah, I love the evidence statements a lot because they're super informative and give a lot of examples of what students should be doing in class, and they're scaffolded, and I'm just in love. And then we're going to talk about COVID-19 clusters and data for next year. So what's a good phenomena? Let's talk about that first. So a good phenomena is something that students need to answer the question. So it's novel. If you've used an anchoring phenomena in your classroom or in lessons, that is not a good phenomena for you to use for assessment. You're looking for students to make sense of something novel that they've never seen before, doing what scientists do when they look at new things. So make sure it's novel and it's relevant. Anything is a phenomena. My desk that my computer is sitting on is an example of a phenomena, physics and probably life science and maybe earth science. But we want to make sure that it's really relevant and also interesting. And interesting does not mean shock value, like it doesn't mean something's blowing up or being eaten necessarily. It can be, as long as it's relevant and interesting, you're onto something good. And it has to be explained by the application of science knowledge. So finding phenomena is really important because we're looking to get your students an opportunity to apply what they've learned previously through the unit or series of lessons that you just went through. So you need to find a phenomena that can be answered by the application of knowledge. So we're going to look at a good phenomena and a not so good phenomena. I'll let you decide which one you think is which. I have my own opinions. So first, is this a good phenomena? Do students need the phenomena to answer questions? A boiling pot of water. So this is one that we've had teachers send us probably 20, 30 times. Model how heat changes molecular motion. A couple comments on this. So it's not a specific instance. This is a general common example of what's going on. Really, this is probably recall or representing knowledge. Even though students are drawing a model, and that's what we're asking them to do, this isn't the actual modeling SEP. What we're doing right here is figuring out if they can draw a model, and most likely students have come across the heating of water molecules at some point in their studies, and so they'll just be recalling what they've already learned. If you want this to be an application-based and sense-making based assessment, then you need to have a new phenomena that they've never seen before to make sense of. So I think that this is not a good phenomenon. Now, is this a good phenomenon? So hot air balloon. Use a model to show how heat and molecular motion explain the balloon's movement. This is a specific instance. This is a real thing that happened. There's a balloon flying up, there's fire, and then the bottom drops out, which is probably absolutely terrifying for all of the people involved. But for us as scientists, we can analyze it and see what happened. It's probably novel. I doubt your students have seen this GIF before, and they're applying concepts of density, of particle motion, kinetic energy, and all of that to make sense of what's going on. You have to see this model in order to answer questions. We love phenomena like this. Not coincidentally, our website has this phenomena on it with a bunch of questions on molecular motion and all that. So now we're going to talk about DCIs for diagnosis. I'm happy to talk more about InnerOrbit, and throughout this, I'll go through it. What we're going to talk about right now is mostly looking at what students should have known before they were in your classroom, and then what they should know now, and maybe even the path towards where they're going in the future. The progressions are what we're looking at for these DCIs, and they build from K through 12. What I recommend doing as a diagnostic assessment or something at the beginning of your formative or summative assessment is to write a few questions that assess background knowledge. What gaps in understanding do you anticipate from prior grade bands? If you're a elementary, a middle, or a high school teacher, there are things that your students walk in that you're supposed to cover and that they're supposed to have learned that they just didn't or forgot or whatever. So we strongly recommend that you look at these progressions to look at what students should have learned in prior grade bands. So Achieve did a phenomenal job with this. This is one of the appendices for the NGSS. This is looking at PS1A, the progression. So in 3.5, we just know that matter is particles that are small, and you can measure properties to identify things. In 6.8, it goes a little bit farther. So matter is composed of atoms and molecules, and those can be used to explain properties of substances, and states of matter, phase changes, and conservation of matter. In 9.12, we get into subatomic structures, interactions between electrical charges, etc. It gets much more complicated, and in 9.12, we start to talk about the periodic table. If you're talking about the periodic table before 9.12, that's something that students should only be going over as they learn about electrical fields and subatomic particles, etc. San Diego County in California has a spectacular website, and you can look up each of the DCIs and see what performance expectations they're associated with. So for PS1A, there are PEs in K2, 3.5, 6.8, and 9.12 that are associated with this DCI. And inside each of those performance expectations, there are elements. So I just want you to pay attention to the purple highlight here. So for PS1A, there's one element in 5th grade that students should know, and it's that measurements of a variety of properties can be used to identify materials. So this really specific element is something that you can ask a question about in your assessments to get an idea if students have the background knowledge they need in order to access a 3-dimensional question around this. Really important that we're not having students draw models before we know if they understand the underlying concepts behind those. In InnerOrbit, we work very hard to write questions that are highly aligned, and we use these progressions for DCIs to show you data on student progress. So for PS2A, and this is an actual assessment and an actual report in our platform, we identify in 3.5 there are elements that students should have learned, in 6.8 and in 9.12. Everything with color, so the 47% in 3.5 and the 35% in 6.8 and the 97% were all elements that were assessed, and everything else has not been assessed yet. So we know by looking at this report, students struggled with the idea of vectors. They struggled with force pairs, but they understood net force. So our goal is that throughout one school year, unit, lesson, or multiple years, that we can track students' progress on a DCI, an SEP, a cross-cutting concept, or even the evidence statements over the course of time to measure how well they're doing in their progress towards a performance expectation. The DCIs are a great base for students to use to then, hop up and apply those cross-cutting concepts and SEPs. Now we're going to talk about the rest of the progressions, mostly focused around rigor. So for the SEP modeling, and I blacked out most of this because I don't want it to be overwhelming, there are elements that students should be doing in 3.5, in 6.8, and in 9.12. So in 3.5, students collaboratively develop a model, and I'll go to the next slide to walk through this. But I'm showing this to demonstrate there are many elements in the SEPs for 3.5, 6.8, 9.12 that students should be doing. And we want to make sure when we're writing questions that we can write some questions for the prior grade band, but we really want to focus on our grade band and make sure that we're not making things too complicated by jumping up. You know, if I'm a 6.8 teacher, I don't need to jump up to 9.12. So in 3.5, students should collaboratively develop or revise a model. So independent modeling in 3.5 would be a little bit more than what the standards are asking you to do. You can do it, they can do it, great practice for 6.8, not required. We're looking for relationships among variables for frequent and regular occurring events. In 6.8, now develop a model. So students are doing this independently based on evidence to show what happens if a variable or component is changed within the system. So now we're looking at change. In 3.5, it's regular occurring events. In 6.8, it's a change. So what happens if there's additional sunlight, the temperature is higher or lower? How does that impact evaporation? And then in 9.12, now we want you to develop, revise, and use a model to predict relationships between systems or components of a system. So now instead of just looking at one system, we're looking at multiple systems and the interactions between the two. So when water evaporates from a cup, given higher or lower temperature, what does that do to the, the atmosphere and the composition of water in the atmosphere? And what do those higher temperatures mean on a more global scale, the interactions between the hydrosphere and the atmosphere? So the cross-cutting concepts do the same thing. So patterns of change can be used to make predictions, and then patterns in rates of change and other numerical relationships. So now we need a numerical relationship between those things, can provide information. And then now we're looking at scale, and actually the scale of a pattern, and if that can be used for a relationship. So we might look at molecular scale patterns. We might have to look at global or even greater than that scale patterns in order to get the information we need to explain phenomena and to have evidence that's ample to do that. So I show all of these to you to make sure that you see what students should have been doing in 3.5, what they should be doing in 6.8, and then what they should be doing in 9.12. It's perfectly okay to go a little bit beyond to give students practice for the next grade level band, but we want to make sure that when we're, if we're in 6.8, we can't just ask students to make a prediction. To be aligned with this, we want them to also look at rates of change and numerical relationships. So what if this changed at 2x the rate, at half the rate, etc. Now we're going to talk about the evidence statements. I love the evidence statements. I'm not ashamed of it. I'm not embarrassed. So the evidence statements are amazing. If you go to the Achieve website or you Google search for evidence statements, MSPS 1.1, this will pull up. And I want to go over how these evidence statements are structured to provide you with some scaffolding for writing clusters of questions. So the first part of evidence statements details kind of what background knowledge students need, what basic knowledge and or skills they need. So for this, we're looking at, what do students need to describe chemical reactions? And it gives a line item list of each of the things that students should know. This isn't an absolute checklist, but they're suggestions for things that we could assess given the context of what you've been going over. The middle evidence statements, and I'm going to be a little vague about this because the evidence statements have many, many parts. The middle evidence statements are really focused around getting students to show relationships between things. Sometimes it's making connections between things. It's usually two-dimensional, maybe some three-dimensional items in there. They're not making sense, but usually they're recalling relationships, between patterns of this change versus that change, something to demonstrate that energy transfer can occur by molecular collisions is a good example of. These are relationships between two different things, the energy and the transfer. At the end of the evidence statements, the final elements, are sense making. These are the actual three-dimensional parts of the evidence statements. Students are incorporating SEPs, they're incorporating DCIs and cross-cutting concepts. So not just showing a molecular collision, but they're showing how this phenomena demonstrates that molecules collide and transfer energy outside of a system during a chemical reaction. We love using these, and we use these to write all of our question clusters. I strongly recommend that you look at the evidence statements when you're writing assessments and use those to write clusters of questions. First, assessing DCIs as background knowledge, then incorporating some of the cross-cutting concepts in the middle parts of the evidence statement, and then writing three-dimensional questions that align to some of these bullet points in here, or all of them at once. Now we're gonna look at some example clusters. So we have hundreds of phenomena and clusters of questions on InnerOrbit. We would love for you to sign up. It's, again, totally free until August 2020. And yeah, we have lots of these clusters and lots of phenomena that we work very, very hard to write. What's a cluster? Clusters are groups of questions that are built around a phenomena. We write clusters that are usually between 1 and 10 questions to assess a performance expectation, which is a complex thing that students should be doing at the end of a grade level band. So at the end, not just at the end of the year in your classroom, but at the end of 6-8, at the end of 9-12, they should be able to demonstrate proficiency in these. We recommend that you write clusters of questions. So the evidence statements and the elements that we looked at for DCIs or cross-cutting concepts, those progressions, are excellent tools in helping to write these clusters of questions. And I'm going to show you some examples of how this works. So one of the phenomena that we have on our site is how do light and water impact spearfishing. This is a light waves assessment and phenomena. And we're looking to see, all right, so we have these guys throwing spears into the water. And then in another GIF on the right-hand side, it looks like the spear is bending in the water. Weird. If students have learned about refraction and learned about how light waves change when they travel through different media, then this is going to be super, super helpful in having them apply that and see, exactly how well they're able to make sense of something novel. So our first couple questions in a cluster of questions revolve around background knowledge. And these are DCI only questions. So it's called blank when light changes direction as it enters the water. Do you know what refraction is? Yes or no? The second question is, if a person threw a spear along the dotted line and we have an image of this dotted line, then they would blank the fish because the water changes blank. Do you think it changes the angle of the spear, the angle of light waves travel, reflection of light, the interference of light waves, etc.? So this is just going one step further in the DCI to say, okay, there are some patterns here. If you throw a spear along your line of sight to a fish, that you may not end up hitting it. I'm kind of giving away the answer. I feel bad about it. So how do light and water impact spearfishing? Now we're going to get to a three-dimensional question. This is at the end of the cluster. And after this modeling question, there's also a free response question where students explain their model. So all of the standards tagged on the right-hand side here align to both this modeling question and the free response question below it, which asks students to explain their model. So now the image below shows where the fish appears to be to the person. Draw another fish to show where the fish actually is in the water. Draw a second line to show how the fisherman will have to change their aim to catch the fish with their spear. So now we're giving students a phenomena and having them make sense of the fact that that spear appears that it's bending in the water. We want students to model, so they're developing using models. They're applying what they've learned to something novel. Hopefully they have not studied spearfishing in their private or academic life. They're definitely applying aspects of the DCI electromagnetic radiation, and there are also elements of structure and function of the water and the composition of those particles and how those interact with air. And so the question below this is explain what scientific concepts allowed you to draw the fish where you did, and explain was that reflection, refraction, absorption, transmission, etc. So this is an example of a cluster. We have a couple more questions in this cluster as well, but this is a good place to start, where you give students a couple questions to assess DCIs, maybe throw in some patterns with your second question, and then later on get into questions that are three-dimensional, where students are modeling and they're showing what's going on. Let's look at a second phenomena as well to see how we wrote a cluster around this. So this is a chemical reaction phenomena. Is there evidence of a chemical reaction? Both of these are middle school phenomena, and these are middle school clusters of questions. So in the above GIF, we see a piece of iron. It's gaining mass as it burns. And in the GIF on the right-hand side, or GIF, I don't know how you think that's supposed to be said. But those are, there's a time lapse of water over 10 days, and it also changes in mass. And the question is, can you use any of this evidence to show that there has been a chemical reaction or not? And we do state to students that the iron wool cannot be burned a second time after it's burned the first time. So kind of a spoiler, I guess. So in the first couple questions, we say the change in weight of the iron wool is an example of a blank change. Do you understand that change in weight is a chemical or physical change? If the iron wool can no longer be burned again after it's burned once, this is an example of a blank change. So now we're just assessing, do you understand the differences between physical and chemical changes? After that, we ask another question where one of your classmates makes the following statement. So now students have to go through and evaluate a statement by an imaginary classmate. They need to say if something, this one is physical or this one is chemical because the change in water is this and the change in iron is this. And they have to say that the statement that the student made is true or false. At the end of this cluster of questions, we have the actual three-dimensional CER statements, the real juicy stuff. So now write a claim supported by evidence and reasoning that answers the following question. Is the change we observe in the iron wool a chemical reaction? And then the second CER statement, because there are actually two phenomena in this, is the change we observe in the water a chemical reaction? So students have to pull evidence from this, cite things that they've learned in class, and write a CER statement, which is part of constructing explanations and designing solutions to explain their change. Awesome. So now let's talk about COVID-19. Super fun times. I just want to take a second to thank you all so much for taking the time to be here. It is phenomenal to have you here. And I'm really proud of you for stretching yourself and putting in time for professional learning. I'm grateful that you've chosen to spend some time with us. I know you have a lot of competing priorities right now. If there is anything that we can do to support you with your classroom, I can't give you like a back rub or anything right now, though I would like to, because you probably deserve one. Things are tough. So let's talk about how we're thinking about assessing during the COVID-19 era. So multiple choice equals good. One of the things we're doing right now, we're going through our whole site and we're adding in more multiple choice questions in every cluster we possibly can. The reason for that is that, well, we'll get to that in a second. And multiple choice allow you to gather data around student understanding. So all of those beautiful reports that we saw earlier on students' understanding and progress towards the standards. We strongly recommend that you assign multiple choice questions and you gather data. This will help your teachers next year. It'll also help prep you for next year if we end up in some sort of digital learning situation next school year as well. We want you to have this kind of data on your students, their progress, and be able to give this data to the teacher where students are going into their classroom, especially if there are standards that you were supposed to teach at the end of the year and your district has mandated that no new instruction will occur. There's also a lower potential for academic dishonesty. When you have multiple choice questions, it's kind of a low lift for students, lower lift. And so you're most likely going to get those students answering from their own brains. It may not be worth it to Google a multiple choice question. There's no grading time. Yay. So if you use InnerOrbit, or many people mention Google Forms, I strongly recommend that you use multiple choice questions because you have a lot on your plate and you're just trying to get students learning and logged into Google Classroom or Canvas or whatever you're using. So don't add on extra grading that's unnecessary. I recommend that you use multiple choice questions as often as possible. So on that note, for responsive modeling, skip or extra bonus. And I'm not saying extra bonus like give students extra credit for doing those things. I know that normally we would say free response questions and modeling questions are the only way to properly assess an NGSS standard. So students should be explaining what they've learned and why it applies to a phenomena. But in this context, I would say skip the free response and stick with the multiple choice. It's extra grading work for teachers, for you all and the teachers that you support. It's also not equitable because it's just impossible to monitor all of that if you're not there physically present with them. Just one more plug for InnerOrbit. It is totally free until August. If you go to InnerOrbit.com and sign up right now, you can check out the platform, check out the phenomena and the questions, try it out if you want as a free pilot up until August. It's free until August. That concludes our webinar. Send me an email if you all have any other questions. Take care.